Okay, so it's 1 o'clock, and welcome to, well, basically our last time together. Tuesday is the last day of lectures, and I thought we could have a bit of a review session. And so let's see, what to do for this review. Well, there's lots of things we could do, but I thought maybe the most useful thing to do, because that the quiz yesterday and maybe throughout this morning is sort of fresh in your mind, and maybe it would be helpful to go through a couple of points. So, I'll post the solutions and all that, and you already know sort of your results, I guess, for the multiple choice. But I think it's always useful, even if you have like a posted solution, to have someone sort of walk through that solution, because there's a lot of interesting physics going on and a lot of points to make and things to talk about, and along the way, what I'm hoping is you guys can just ask me some questions, interrupt me. So just feel free to interrupt. It's really hard for me to see the chat at the same time with the screens that I have, and so if you have a question, just unmute yourself and say, hey, hold it, what about that? And then your question is probably a common question, and then we can address it. It just makes it a little bit more fun as well, I think, for everybody to have a bit of questions going throughout. Anyways, so let's look at quiz 6 here. So in this first question, we have a merry-go-round. And it's a little bit different from the other merry-go-round questions you've had, which were something like you've got somebody at the edge of the merry-go-round going around, and then they walk towards the center. And when they do that, they're reducing the moment of inertia of the system, and so the angular velocity of the system goes up, as does the kinetic energy, but the angular momentum stays the same. It's that kind of thing. Here we're doing, instead of walking radially inwards, we're talking about walking around, tangentially around the merry-go-round. Okay, and so the picture looks something like this. So we start with a merry-go-round, and this is looking top down. And the idea is this merry-go-round, this is the center here, and it has some moment of inertia, ICM. Okay, and we've got this guy initially standing at the very edge of the disk like this. And that guy has some mass m. And everything starts off at rest, and so the initial angular momentum in the system is 0. And then what the guy does is he starts to walk counterclockwise around that merry-go-round. And so when he does that, he's going to exert a force in that direction on the merry-go-round. And so, because he's pushing himself forward, so he's pushing back on the merry-go-round. And so that backwards force, if we take this R cross this backwards force that he exerts on the merry-go-round, R cross F there is a torque into the board, into the page, and so it's going to cause an angular acceleration clockwise. And so that disk, that merry-go-round, is going to start to rotate clockwise. But, that force that he applies to the disk, well, there's an equal and opposite force, F12 is minus F21, acting on him. And that force is up like that. And you go the same R across that new upward force is a torque in the counterclockwise direction, pointing out of the page. And so that's what's going to cause our person to get some angular momentum, get some angular velocity and angular momentum in the counterclockwise direction. Okay, and so while he's pushing, he's accelerating himself. But now let's suppose that he's come up to speed and he's walking with just a constant speed around. So sometime later, the situation will look like this. Person will be over here, and that person will have some speed. They'll be moving at some certain number of meters per second in a tangential direction, so they'll have a speed v. And that's a speed v relative to the ground. Okay, and associated with that speed v relative to the ground that's a tangential velocity. There's also an angular velocity. And so our person here, who has mass m, we'll suppose has an angular velocity, omega m, which is positive. Okay, so we'll take counterclockwise rotations to be positive. Okay, so that's great. And that tangential velocity v in meters per second is related to the angular velocity omega m by, v is equal to r times omega m. Okay, so that's going to be an important relationship to begin with. Okay, so that describes the person. Okay, and then the disk, the merry-go-round, because of this force down or a torque in the downwards direction, it's going to have caused that disk to pick up some angular velocity in the clockwise direction. So the disk at the end of the day, when he's moving with a constant speed around, is going to be rotating in the clockwise direction with an angular velocity, we'll call it omega, about the center of mass. And that's going to be negative. Okay? And then you say, okay, so what are we going to do? So basically, we're going to say, first of all, it doesn't matter how fast that person, that person could have started at rest and is walking slowly, or that person could have started at rest and is walking really fast. Okay, so when the person's walking really slowly, that person has a small angular momentum in the upwards direction, counterclockwise, and the disk has an equal magnitude opposite direction angular momentum the other direction. If he's moving faster, then the disk is also moving faster. But in total, the angular momentum always remains 0. It started out at 0. Okay, and so you say 0 is the initial angular momentum, and when the angular momentum is positive, well, then we're talking about a counterclockwise rotation, or the vector, angular momentum vector, is up. So the initial angular momentum is 0, and then that has to equal the final angular momentum, and that's because we have that the sum of the torques is equal to 0. Okay, there's no net torque on the system. Now, of course, there are internal torques, right? So when our person pushes with his foot downwards like that, that's exerting a clockwise torque or downwards torque vector on the disk. But at the same time, the disk is pushing back on the person, and that's exerting an upward or counterclockwise torque on the person. So torque 1,2 equals minus torque 2,1. And when you add up those torques, you just get 0. It's like F12 equals F21, so minus F21, so when you add them up, you get 0. All the internal forces in a rigid body cancel, and here all the internal torques cancel. And then external torques. Well, there's no external torques because the only way our system is person plus merry-go-round, and the only way that our person and merry-go-round are connected to anything else is through this shaft, through this frictionless shaft. And so there's no way that the Earth, or there's no way that that as the merry-go-round turns, it doesn't exert any twisting force on the Earth. And so there's no angular momentum transfer to the Earth. And similarly, the Earth can't exert a twisting force on the merry-go-round. And so there's no angular momentum transfer to the system. So no angular momentum in or out means whatever angular momentum you started with, it has to stay the same. So L initial equals L final, right? And then we just need to figure out, well, what is L final? Well, for L final, so angular momentum is, I times omega. And so there's angular momentum counterclockwise or positive angular momentum in the person, and clockwise or negative angular momentum in the merry-go-round. So for the person, we just go I omega. So I for the person is mr squared. That's just a point mass, m, located at a distance r away from the axis of rotation, just mr squared, moment of inertia for the person, times their angular velocity. And their angular velocity is omega m. And this omega m is positive. Okay, and then we add to that the angular momentum for the disk, or the merry-go-round. And so that's going to be ICM, the moment of inertia for rotation about the center of mass, times omega cm. And omega cm is negative. You don't know what it is, but it's negative. And so then that positive and that negative, they have to add up to 0. Started out at 0, always stays 0. Okay, so that's the first equation. That's conservation of angular momentum. And so we have one equation and two unknowns. We don't know what omega m is, and we don't know what omega cm are, whatever. Okay, so then the second thing is we need to give... Yep.
Okay.
Yes.
Your video is kind of covering part of what
sorry.
you've written.
Sorry. Yeah, I see that now. Let's pull this over here. Okay. Great. So we don't know what those two unknowns are. We need one more equation here. And that equation comes about because we haven't yet said how fast this person is walking. Because if the person is walking really fast, counterclockwise, well, then the disk will be rotating really fast clockwise. If he's walking slowly, so, omega m and omega cm, they depend upon how fast the person's walking. Okay, and so then we give this interesting constraint. It's like a relative velocity constraint. So we say that the relative velocity, so this is the velocity of the person relative to the disk. Okay, I'll call it the disk. It's shorter than merry-go-round. So it's the person relative to the disk. And so what that means is that person is walking along, and he sees that disk, rotating under him, and he sees the disk moving moving behind him at a certain number of meters per second. And that's the relative velocity of the person relative to the disk. And that's what we're going to be given. We're going to say, well, this person, when this person is normally walking along the road, they can walk with a speed relative to the road of, say, 3 meters per second. Well, we're going to say the same thing here. The guy starts walking, and he walks such that the road beneath him is moving back at 3 meters per second. That's the relative speed, okay? And so what is that relative speed here? This is the thing that we know, and then we can express that in terms of our two unknowns, omega m and omega cm, okay? So the relative velocity, well, I don't know. The relative velocity is the velocity of this person relative to the ground, so that's just v, which is r omega m. That's this velocity minus how fast the ground is moving behind him. And so that's the velocity of a point on the disk. How fast is a point on the disk moving backwards like that? Okay, and so you go subtract. So how fast a point is moving backwards here is going to be just r times the angular velocity of the disk. So if the disk is rotating slowly clockwise, then that tangential speed of a point on the disk is moving slowly backwards. If the disk is rotating fast, well, then it's fast. And so that's r. Tangential velocities are always r, the radius, times the angular velocity. Okay? And so remember, this guy is positive, and this guy is negative. So you're going minus a negative, so it makes it even bigger. Because if the disk is rotating clockwise, well, then the relative velocity is even bigger. Right? It's in the negative direction. So you have to go something minus a negative. It makes it bigger. Okay, so that's that. And so that's equation 2. That's our relative velocity equation. And so now we have two unknowns here, omega m and omega cm. Okay, so now we have two equations and two unknowns, and we're basically done. Now we just solve. Okay, so let's actually go through the solution a little bit. Okay, so we start off and we say, yep, well, what is v? Well, we know that v is, this is the thing which we're trying to solve for in the end. What is v? Well, we know that it's r times omega m. Okay, but we know, well, wait a minute, here's r times omega m. So we can express that as v relative, and then take this guy to the left-hand side of the equation, plus r times omega cm. Okay, so we've got an omega m here and an omega cm. We want to express the whole thing in terms of either all in terms of omega m or all in terms of omega cm to get one equation and one unknown. Okay, so then we go back and we say, well, can we express omega cm in terms of omega m? Well, yeah, we have the conservation of angular momentum equation. So omega cm is omega m, and just invert this equation. So we get v relative plus r times omega cm is a negative mr squared over ICM times omega m. Okay, so now we've got an omega m here, and we have an omega m here. And in fact, what we have is, this is the same thing as v, this is v, is equal to v relative, that's this, minus, and if you look at this, r times omega m, well, that's just v. So what is times v? Well, this thing. So minus mr squared over ICM times v. So now here's v and here's v, and we have one equation and one unknown for what we're looking for. So we just collect the terms multiplying v. So on the left-hand side, there's a 1, and then we take this thing over to the, take the thing on the right-hand side over to the left-hand side. So that becomes plus mr squared over ICM times v is equal to v rel. Okay, and so we finally get that the speed that the person is walking at relative to the ground is proportional to the speed relative to the disk by this factor. It's 1 over 1 plus mr squared over ICM times V rel. And so then we get that. And we notice that this answer for the speed is less than V rel. Okay, so this person is walking with some speed, maybe like 3 meters per second relative to the disk, but the disk is rotating clockwise, and so the person's speed relative to the ground is less than that. How much less? Well, by this factor over here. Okay, and so you always have a dimensionless ratios. This is the moment of inertia for the person. This is the moment of inertia for the disk. Okay, so then we have sort of two special cases. So I guess this is two special extreme cases. So that's part A. And then part B says, well, let's look at those extreme cases. So let's suppose that the moment of inertia of the person, that's this guy over here, is large compared to the moment of inertia for the disk. So let's suppose that mr squared is way bigger than ICM. Okay, and so what that corresponds to is the person is really heavy and the disk is really, really light. Imagine it being made out of paper. Okay, and so if this guy starts to walk, that paper is on a frictionless axle. You can easily spin that piece of paper up. And so what's going to happen is the person, because remember that the person is applying a force to the disk, and the disk is applying a force to the person. And those forces are equal in magnitude. But the person's mass is way bigger, and so the acceleration will be very small. So the person should be moving slowly relative to the ground, whereas the disk is moving fast relative to the ground. Okay? So in that case, what we expect is v goes to 0. And that's right, because if you take if mr squared here on the right is large compared to ICM, then you have 1 plus a large number in the denominator, so it's small. So in this case, we get that v approaches 0 in that limit, which is correct. And then the other extreme case that's interesting to look at is, it's always interesting to look at the extreme cases and then see if they make any sense. Because if the extreme cases don't make sense, you've made a mistake in your algebra somewhere, or your intuition isn't good. One of the two, right? And what you want is your intuition to start lining up with the math, right? That's part of the whole exercise, right, of learning physics. Okay, so mr squared is much less than ICM, so that means you have a super light person on a really heavy disk. Well, when that guy pushes against the disk, because the disk is so massive, it's barely going to move backwards. But that same force will cause that person to accelerate up to the speed v. And so at the end of the day, we got a person walking around with basically a speed v relative compared to the ground, because the disk is barely moving, is barely rotating. And so in that case, we should have that the speed relative to the ground approaches just the relative speed. And that's right, because if mr squared is really small compared to ICM, this thing is basically 0. So it's 1 over 1 is 1 times v rel. Okay? So that's the idea for that thing. Does this make sense so far? Does anyone have any questions? Just like unmute your mic and, yo, what are you talking about? We're good? Okay. And let me know if this is not useful and if we could do something else as well. Anyways, then for part C, what we now have, and this is sort of always the case, as soon as we know, initial moments of inertia and initial angular velocities and final, well, then we can figure out changes in kinetic energy. Because, I mean, if you think about it, there was 0 kinetic energy to begin with, and then after a little while, this guy's walking, so he's got some kinetic energy, and the disk has some kinetic energy. So all of a sudden, some kinetic energy was created. How did that happen? Where did that come from? Well, that came from this chemical energy, right? Just like when you're starting at rest on the road and you pick up speed. Okay, so you've got some kinetic energy. Well, that came from your chemical energy, right? You're doing work. Work is energy transfer. Chemical energy is being transferred into kinetic energy in this case. Well, how much? Well, you need to figure out, you can figure that out now. Okay, so basically you need to know both final angular velocities. We've already figured out omega m. So these were our two unknowns. We figured out omega m, because omega m is basic, because we figured out v, and v is just r times omega m. So we figured out omega m. We need to figure out omega cm. We need to figure out the angular velocity of the disk. Okay, so first of all, from part A, we know that omega m is just v over r. And here's v, so we know it in terms of v rel, the main parameter we're given, right? And then the other thing we need to figure out then is omega Cm. Okay, so omega Cm, we go back and, oh, omega Cm can be expressed in terms of omega m just using this conservation of angular momentum equation. Okay, and so you get omega Cm is equal to negative mr squared over ICM times omega m. Okay, and then we say, yes, but this is the same thing as negative mr squared over ICM, and then what's omega m? Well, omega m is just v over r. Okay, so this is omega Cm. Okay, so now omega m and omega Cm are both expressed in terms of v, and we know v back here. Okay, and so now that's great. Now we can calculate the change in the kinetic energy. Right? So I won't go through that calculation. So change in kinetic energy is kinetic final minus kinetic initial. Everything started at rest, so kinetic initial is 0. And then kinetic final is just 1/2 I omega squared for the person and the disk. Okay, and so we know everything. And so we crank that out. And the answer that you get after a little bit of algebra is this same factor, this ratio of moments of inertia for the person and the disk, that's the important thing in this problem, times 1/2 mv rel squared. Okay, so this is an interesting result. So it says that the amount of kinetic energy, the amount of chemical energy converted into kinetic energy, is basically 1/2 mv rel squared. Now that's what you would expect if a person is just walking on the road, right, and he picks up speed to some speed v rel. The kinetic energy is, well, 1/2 mv rel squared. Okay, but now it's less than that because of this factor over here. Okay, because as he's walking, as he pushes himself forward, the disk goes back. And so now there are two things in motion. Okay, and so there was a special case that you could look at here that's kind of interesting, is let's suppose that, I think this was part E or whatever. You know, you can say, well, suppose that ICM is much less than, let's see if this agrees with our intuition. So ICM is much less than mr squared. Suppose that's the case. So that means that we've got like a heavy person on a super light disk made out of paper. And so that person starts to, tread their feet like this. And like I said, equal forces on both objects. But because the disk is so much less massive than the person, the disk right away spins up to basically, be relative. And this guy just basically stays in place. And so if he stays in place, well, then his speed is or almost in place. His speed relative to the ground is very small. So his kinetic energy relative to the ground is very small. 1/2 mv squared is very small. But the disk, even though it's spinning pretty fast, who cares? It's got such a small moment of inertia that 1/2 I omega squared, even if omega squared is something not zero, I is so small that it basically goes to zero. And so there's no kinetic energy in the system. And that's right. If we look at this expression, if we let ICM become really small compared to mr squared, this is really small. So 1 over small is large. So we have large in the denominator, 1 over large is small. And so this delta kinetic energy goes to 0. And it agrees with our intuition, with our common sense, right? That's how you check your answers. Because remember, it's only in physics courses that you have, solutions. When you're actually trying to solve problems in the real world or do research or whatever, you don't have back of the textbook to look at what the answer is, right? You have to be able to check your answers yourself and convince yourself that it's right, that you haven't made a mistake. Anyways, so that's sort of that problem. Is everyone okay with that? Does anyone have any questions about that? Am I going too fast? Is this useless? What are your thoughts? Keep going or stop going?
So just to confirm, so when you're talking about conservation of angular momentum or linear momentum,
Yep.
You always have to look at the speed values relative to the ground, or the Earth, because the Earth is the one that's the inertial reference frame.
Yeah, that's right. So you need to pick an inertial reference frame. It doesn't matter what it is. Once you pick it, just stick to it, and then it will always be true. Conservation of energy and momentum and angular momentum. These are all conserved quantities, and they're easiest to work out in an inertial reference frame. So in this case, when we're talking about energies, and that's a good point, because when we're talking about kinetic energy is not a conserved quantity, right? Kinetic energy is conserved, but energy can take many different forms. You know, gravitational goes down, so kinetic goes up. You know, but kinetic itself is not a conserved quantity like total energy. And kinetic energy has this weird property. It depends upon your frame of reference. Okay, so here I've got a box with some mass m, and that thing is just sitting there at rest with respect to me, and I say, oh yeah, that thing's got like 0 kinetic energy, right? But then all I have to do is move to a frame of reference that's moving with the speed v to the right, let's say. So now the box is at rest, but now I'm drifting to the right. Well, from my point of view, that box is drifted to the left with the speed v, and suddenly it has a kinetic energy 1/2 mv squared. Had no kinetic energy to begin with, I just changed my frame of reference and it has kinetic energy. So kinetic energy is not sort of an invariant thing. It depends upon the frame of reference. So in this problem, what we're doing is we're saying, well, we're going to be measuring kinetic energies. And so we'll go from the frame of reference in which we started where everything was at rest. And so relative to that frame of reference, if we start to move in that frame of reference, if the person or the disk starts to move in that frame of reference, now we've got masses in motion. And those velocities, when you go 1/2 mv squared, those velocities are relative to the initial inertial reference frame you started in and stay in. Yeah?
Yeah, makes sense. Thank you.
I mean, you could analyze the entire problem from the frame of reference of the rotating disk. You know, someone sitting on this rotating disk, and it becomes more complicated. Easier to stay in the inertial frame of reference and look at everything in relative to that. Okay, so the second question was the famous Tippy Bridge question, and my feeling is we've sort of beaten that question to death. And I mean, we could go through it, but my feeling is that maybe we've already done a lot of that. But if anyone has a particular question about question 2, something that didn't make sense, or fire away, and we can have a look at it. Right? So I'll just sketch it out. Remember, we had this fridge like this with 2 little feet at the bottom on level ground. And then some guys pushing like this with some force, horizontal force like that. And, the question is, how much force do you have to apply so that this leg here starts to lose contact with the ground. So in other words, this normal force, which when this force is 0, the normal forces are balanced, they're each equal to 1/2 the weight, right? But then as the guy starts pushing, then this force goes down. Sorry, which one goes down? Yeah. Ooh, this is really weird because when I look at myself, it's like, whatever, mirror reflected. So, okay, I'm not going to look. Okay, so when there's no force applied, then the normals are both equal to 1/2 the weight. But when you start pushing like this, then the weight on this leg gets reduced, and the weight on this leg increases, till eventually all of the weight is on this leg, and none of the weight is on this leg. So this that goes down, and that goes up. And then you're looking for this normal force n. You're looking for the condition n is equal to 0. Anyway, so I hope that that's okay. And in the end, you discover something kind of interesting. You discover that in order for, suppose that mu s is equal to 1. So it's a pretty sort of high friction floor. Then then in order for this fridge to slip before it tips, because that's what you want, right? You want it so that even if you push in the worst scenario or worst possible case is you push the very top of the fridge, and then that's going to be most likely to knock the thing over. And so even if you're pushing way at the very top corner like this, sideways, okay, you want to figure out, well, what's the ratio of height to width that's going to guarantee that this fridge is going to slip before it tips up like this. Okay, and the answer is, well, it has to be twice as wide as it is high. So it's a pretty low squat fridge. Okay, so typically It just tells you that typically fridges will tip before they slide, before they slip, tip. Oh, I can't speak today. Okay, so is that good? Any questions about that one? Okay. So let's look at some of these multiple choice questions. So I don't know what happened on the multiple choice this time. You guys did really well on the multiple choice last time, like 75 or something like that. This time it was like 53 or something. I don't know, I'm not exactly sure why. So, so for this first multiple choice, a lot of you got the wrong answer, and I'm wondering a little bit why. So we got this object here. It's some object, and it's got some momentum like this. And that momentum is constant. And so this thing is just moving along a straight line with constant speed. And it'll just do that forever. And then we're asked, well, what is the angular momentum of that object in linear motion about this point over here? Okay, point O. Okay. And so there were some answers, multiple choice answers given. So we called this, we just drew a triangle here. One side is A, the other side is B, and the other side is C. And the question is, what is the right answer? And the answer is A times P, and the direction is into the page. Okay? The question, why is that the case? So remember that angular momentum, the fundamental definition of angular momentum is not I times omega. The fundamental definition of angular momentum about some point O is R cross P, okay, where R is the vector that points from the point O to the object in motion, the object with momentum P. So that's your R. Okay, so you want to work out R cross P. And when you have, say, a rotating object, the only time angular momentum becomes I times omega is when you have a situation like this. So you have an object with a high degree of symmetry, like a disk, okay, and this thing is spinning, okay, with some angular velocity omega. And so then you say, well, if I wanted to calculate the angular momentum of this thing, say, I don't know, say about the center here, what I would do is I would say, well, I got a chunk of mass over here moving with some momentum like this. And so I take this R, cross that P. But when I have another chunk of mass moving with this momentum, so I take that R, cross that P. And I just go around and I divide my object up into a zillion little chunks of matter, each a million, point masses, and I go R cross P for all of them. And so I take the sum of Ri cross Pi. So R1 cross P1 plus R2 cross P2 and so on. And I add them all up. And what you get when you do that, if it's this object of high symmetry here and so on, then it just turns out that that's the same thing as ICM times omega. Okay? But in general, this is not true. You have to do this. And only in special cases do you get something like that coming up. So fundamentally, the definition of angular momentum is R cross P. So in this case, there's different ways to work this out. So let's work out the magnitude. So if you think just about cross product, it's, the magnitude of a cross product is the magnitude of this vector times the magnitude of this vector times sine of the angle in between them. Okay, so if we look, this is R, that's the direction of R, that's the direction of P, and so the angle between them is this one, or equivalently this one. Okay, so now when you look at this picture, you can see, well, as this mass is moving down the line here, moving to the right like this, you can see that R is increasing, but the angle theta is decreasing. It started off here, the angle theta is nearly 90, and then it gets smaller and smaller and smaller and smaller. And so R is getting larger, but sine theta is getting smaller, such that the product, R times sine theta, what is that? Well, that's just, if this is R, and this is theta, then R times sine theta is this side, is A. So that's equal to A times P. Okay, and this is constant. So this mass in motion And it's the same thing as having done the calculation with the particle back here. And this is a right angle. And so this is A, and this is P. Okay, so R cross P in this case is really easy because they're at right angles. This is A times this P, right? So a significant number of you said that the answer is C. This C times P. So remember, it's R times P times sine theta. So the sine theta matters. I guess another way to see this is if this is your R and this is your P, then you can make this R.
You'll need that.
Oh, thank you. You can write R as the vector big R plus, I don't know, let's call this R prime. So then when you go R cross P, that's the same thing as this R is capital R plus R prime, vector cross product with P. And then, but wait a minute, R prime is horizontal to the right, P is horizontal to the right. They're parallel. So R prime cross P is just 0. And so this is the same as capital R cross P. So whether the object is, here, or whether it's further on down the line here, or whether it's here, you'll get the same answer for R cross P. So R cross P remains constant. The angular momentum is constant because there's no torque acting on that thing. The linear momentum is also constant because there's no force. Does that make sense? Okay. All right. Let's see. Let's try another one here. And this one here, the next one was the bicycle tire one. And a lot of you chose D. Depends on the direction of the bicycle tire's spin. So that's not right. So I'm actually kind of a little bit leery about, I thought, well, maybe it'd be useful to go through, quiz 6, but since you've just written it, right, then you're probably thinking, oh, no, I shouldn't have done that. And so, there's sort of regret, but nevertheless, I hope it's still useful to go through. Anyway, so the picture looks like this. So we've got some support here. And we've got a chain coming down, and we've got a bicycle axle. This is the axle of the bicycle wheel. It's horizontal and to the left. And we've got a bicycle tire. Comes around like this. Okay. And there's the spokes. And the center of mass of the whole thing is here. Okay, and so this is the pivot point O. And so we're going to be calculating torques and stuff about that point O. And so the idea here is a person so the chain is holding up the right end of the axle. That's permanently holding it up. And then there's someone over here who's got their hand on the left end like that, holding it up like this. And that bicycle wheel is spinning and everything is fine. And then the idea is the person removes their hand. Okay, so they remove their hand. Okay, and what we know is going to happen is this thing is going to process around. Okay, so the question is, what is, initially, in which direction does the angular momentum of the wheel begin to change? Okay, so the basic idea here is, just like force is the time derivative of the momentum, torque is the time derivative of the angular momentum. Okay, and so if, say, you wait a small amount of time, delta t, then under the action of a torque tau, the change in the angular momentum will be the torque vector times the change in time. Okay, so the key thing is, if the torque vector is that way, then the change in angular momentum is that way. They're in the same direction. Okay, so in this case, what is the torque? So we're calculating angular momentum about the point O and torque about the point O. So what is torque about the point O? So torque about that point O, well, let's see. What forces? So forces acting at a distance, like with a lever arm, they exert torques. Well, what are the forces acting on this wheel? Well, there's a tension up here. That chain is under tension like this. Okay? And there's also gravity acting everywhere on that wheel pulling down. But that's effectively the same as the force of gravity, mg, pulling down at the center of gravity point, which is the center of the wheel here. And so we have this force of gravity pulling down. And this tension and this force of gravity are actually, the tension and the force of gravity are equal and opposite. Okay, so there's no net force, but there's certainly a torque. Okay, so this tension force being applied at the point O, of course, exerts no torque. So that one we can ignore. But of course, the force of gravity pulling down some distance away from point O is, we have an R cross F here. This is the R, and that's the force of gravity. So that torque about the point O is R, half of that shaft to the center of mass, cross force of gravity downwards. Okay, and so when you calculate that, you have an R, which is horizontal like this, and the force of gravity is straight down, so R cross F is coming straight out of the page. It's perfectly horizontal and straight out of the page. So that torque is in that direction. This is coming out of the page at you. Okay, perpendicular to the axle. Okay, and then, and so that's it. That is the change in the direction of the angular momentum. It's coming out of the page, straight at you, horizontal and out of the page. Okay, but then most of you said, or many of you said, it depends on the direction of the bicycle tire spin. So let's talk about that. So there's a couple of things to talk about here. So one of them is that. So first off, let's suppose that the tire is initially spinning this way. Okay, so I curl my fingers in the direction of the rotation. My thumb points in the direction of the angular momentum. So the angular momentum is now, starts off to the left, okay, like this. And then there's been a change in the angular momentum. Under the action of that force of gravity, that exerts a twisting force like this way, coming straight out of the page. And so that's the torque direction, coming straight out of the page. And the change in the angular momentum is in that same direction. So it's a tiny little vector in that direction. This is your initial angular momentum, and you add the change, and you get L final. And so the angular momentum was this way, and under the action of that torque, the axle precesses like this. So this point remains fixed, but this point comes out of the page at you. The left end of the axle comes straight out of the page at you, and it starts to precess around like this. Okay? So that's great. What if the wheel was rotating the other way? So this way. So the angular momentum was initially to the right. Okay, so now we got that situation. So here's our initial angular momentum. And then, gravity exerts this torque, or what's the direction? Oh, this way. Okay, straight out. So the torque is still straight out, horizontal, straight out at you. And the change in the angular momentum is straight out at you. This is delta L. And so L initial was to the right, and then you add a small delta L coming out of the page, and so then this is your L final. So now the bicycle tire, the bicycle, instead of precessing counterclockwise, looking from above, it just precesses the other way, clockwise. So the direction of rotation of the wheel matters to the direction of precession, but it doesn't matter to the change in the angular momentum. The change in the angular momentum is just in the direction of the torque, which is straight out of the page horizontal. Okay, so that's one thing to say about this. And then the other thing to say is, well, and this is something that we talked about a little bit in one of those review sessions. When was that? I guess that was on last Tuesday or something. Anyways, we talked about this a little bit. Was that what the wheel actually does is something a little bit more complicated. So I'll just maybe go through that just a little bit. Okay, so if you missed that, or what is complicated, it didn't make any sense. So what we've got is a pivot point like this, okay, just sticking up like this. And then we're going to stick one axle, the right end of the axle of the wheel on that pivot point. Okay, and so we'll have to sort of draw it in 3D here. So here's the axle. This axle is perfectly horizontal. Okay? And so if that thing were to precess around, it would precess around this circle here, this horizontal circle. So it's just doing this, okay? and your wheel is like this. You know, and there's spokes or whatever. And let's suppose that the wheel is rotating this way. Okay, and so the angular momentum, that's the center of mass. And so this is point O, and this is the center of mass of the wheel. And let's draw the angular momentum vector from O out to here. We'll just make it the same as the axle. Okay, so this is the initial angular momentum of that system. Okay, so you have this axle that's just pointing horizontally, and the angular momentum is perfectly horizontal. Okay, and then you let go. You let go of this end. Okay, and then as we talked about, what actually happens when you let go of this end suddenly, it actually tips down like this. It starts to tip down. So it starts to tip down like this, and actually the tip of that axle, it drops down, but it instantly starts to go over to the side. So it looks like this. The actual trajectory of the tip looks like this. It drops down and then starts going in the direction of the precession. Okay. So let's look at it, for instance, at this point over here, just to sort of fix ideas. The idea is that the torque that's being applied, whether that axle is exactly horizontal or whether it's tilted down a little bit like this, when you go R cross force of gravity straight down, that R tilted down a little bit, cross force of gravity straight down, is a vector perpendicular to this plane. And so it's exactly perpendicular to, it's perfectly horizontal and perpendicular to the axle. So this is really in this plane, in this exact horizontal plane. Okay? And that's the direction of, that's the only direction in which the angular momentum can change. Okay? And so the problem with this, with the tip of this guy falling down, because that's what you would expect it to do, it's going to fall down. And it really does. It starts to fall down like this, but then the problem with that is as it tilts down like this, the angular momentum changed from horizontal to tilted down a bit, so the change is down. So what causes changes in angular momentum is torque. Well, there's no torque down. The torque is exactly horizontal. Okay? And so that can't happen. And so what happens instead then is the wheel begins to precess. And so now, you know, the tip of the axle has dropped down, but it's also starting to move counterclockwise around this circle. Okay? And so what has happened is, because of the precession, remember there's two components of angular momentum now. One of them is the wheel itself. The axle is tilted down, and the angular momentum is not quite horizontal. It's a little bit down, like this. However, because the wheel is precessing, you have a big massive object rotating around like this. So it has gained a component of angular momentum in that direction, that vertical direction. Okay, so because of the precession, it has gained a component of angular momentum in the vertical direction. Okay, and that component of angular momentum in the vertical direction exactly compensates, because remember the wheel is down here, the axle is down here now, so it's got angular momentum like some component down. Okay, that's this component down, but then that component up cancels that component down, so the total angular momentum is the spin angular momentum of the wheel, which is parallel to the axle here, that's this guy, and then you add to that the precession angular momentum, and you end up with an angular momentum that's exactly horizontal. So the angular momentum, even though the wheel is tilted down, the axle is tilted down a bit like this, the total angular momentum of the spin and the precession is still exactly horizontal, and its changes are always exactly this gravitational torque. They're always coming, you know, out of the page horizontal, and then it rotates a bit out of the page horizontal at you. Yeah? Okay, does that make any sense, or did that totally muddy the waters? Did that make it worse? Any questions about that?
I think the angular momentum part made a lot of sense, but I was just curious about what do you specifically mean when you say like something precesses?
Oh, so I mean, so I don't know if you've seen those, I don't know if I can pull up a video here very easily, but so if you take this this bicycle wheel, which is spinning like this, and you hold it up at just one end like this, or have it pivot at just one end, what it will do is the axle will rotate around like this. That's what it means to precess. Maybe I can pull a video up here. Let me see. Where is enter on this keyboard? Yeah.
Hey everyone, it's me, Derek, from the channel Veritasium, and I've been following...
Come on, Derek. Show that bicycle time processing.
The bicycle wheel would already have angular momentum this way, and so a torque pushing that...
Yeah, just show it.
Come on.
There we go.
Oh, look at
That's
that.
precession.
It's rotating as we predicted. See, the angular momentum vector is pointing out this way, but torque is pushing it this way. So angular momentum, torque, and torque is pushing that angular momentum vector around. Except not for long, because this appears to be a quite frictionful wheel. So,
Yeah, Derek. Does that help?
So is the precession like the motion of the axle in a circle?
That's right. Yeah, precession is the motion of the axle. So the wheel is spinning like this, and so there's some angular momentum like this way to the left, horizontal to the left, but also that the axle is precessing. So there's two rotations here. So a spinning thing, like you have a spinning top, and you put the top down exactly vertical, then it will just stay vertical. But if you put it down at a bit of an angle like this, it'll be spinning, but it will also precess like this. So the top spins about its own axis, but then the axis of rotation precesses around. In fact, there's something beautiful about this that Newton figured out. So do you know the precession of the equinoxes? So the Earth spins on its axis, right? There's some tilt of the axis. This is a tiny bit of a tangent here. I don't know that we should do this tangent, but anyways. Here's the angular momentum of the Earth, like it's spinning like this, right? And this is at 23.5 degrees from the plane of from the perpendicular to the plane of the ecliptic, the plane in which the planets orbit, right? So 23.5 degrees. But then what's interesting is that the Earth, because it's spinning, it gets a little bit flattened at the equator, so it comes in a bit. It looks like it gets flattened at the poles and pushed out at the equator. And then you got the moon and the sun. And the moon and the sun, they exert a twisting force on the Earth, a torque, right? Because this chunk of mass gets pulled to the moon with a stronger force than that chunk of mass. And so there's a net torque. And so the torque is in this direction. And so the change in the angular momentum is that way. And so what happens to the Earth's spin? Like you would think that the Earth, it's spinning on its axis, and it'll just point to the same distant star. The axis of the spin will point to the same distant star forever. But what happens instead is, because of what I said, the Earth is spinning, and so the equator gets a bit pushed out, it pulls in, then that extra mass at the equator feels different forces from the moon. And so it exerts a torque. And the torque is in that direction. And so it causes the angular momentum vector of the Earth to precess around. The Earth is spinning fast like this, and very, very slowly the angular momentum vector points to different stars in the sky. So right now, the North Star is Polaris, so it happens to be the spin axis of the Earth points approximately to the star Polaris. But this precession is 26,000 years long. This was discovered by Hipparchus in like 600 BC or something like that, or 200 BC or something like that. Anyway, it takes 26,000 years for the Earth's axis of spin to precess around. And so 13,000 years from now, the Earth's North Star is going to be at 23.5 degrees plus 23.5 degrees on the opposite side of the sky. Right? And you can actually look at the pyramids. The pyramids were lined up with what then used to be the North Star, which has since then changed to a different North Star now. Wow, that was a total digression. Okay, does that help? Are we good? Okay. So let's try another one. So let me see.
I think so. Wait.
Sorry, say again?
The precession creates an upwards change in angular momentum, which counters the downward change created by
Yes.
the thing falling.
Yes, that's right. Where did that go? Yeah, that's right. So you'll notice, like when you actually see demos of this, you start with the axle perfectly horizontal, and you let go, and you see that it drops down like this. In that video that we just saw, you could see the bicycle axle drop down, but that's a problem because that adds a downwards angular momentum component. So then that downwards, the offending downward component of angular momentum is cancelled by the precession angular momentum upwards, because the whole thing is now swinging around like this and has angular momentum that way. Yeah, that's right. That is right. Yeah, there's a lot of beautiful physics in angular stuff. Okay, so there's another one, which was this guy here. So I guess there's a few things to say about this. So you had this spool of thread like this. And so you've got like thread wrapped around a bunch of times. This thing. And like this, and then you pick it off here. And this is a vertical piece of thread attached to the ceiling. Everything starts off at rest. This is the center of mass of the spool of thread. And so what you're going to notice is, oh, well, this thing will start to rotate this way, and the center of mass will accelerate down just like this. Okay, so if we draw it from the side view here, you know, we've got a disk, basically, and we've got a thread coming up like this, and that thread is exerting a tension. So what are the forces acting on this guy? Well, there's a tension acting right at that point, pulling up, and there's gravity acts everywhere, but it's the same thing, effectively the same as the weight mg. And this is a little bit longer than the tension. Mg pulling down like that. Okay? And then so the idea here is basically if you look at, you know, if you go back to our discussion about, you know, linear momentum and all that kind of stuff, if you look at the net force, so if you add up all the forces acting on some object, okay, then that will equal the mass, the total mass of the object, times the time rate of change of, what do I want to write here? In fact, let me just write it this way. It just turns out to be, and we did this calculation, so I don't want to go through that again, but at the end of the day, it turns out to be, the mass of the object times the acceleration of the center of mass point. Okay? So if you look at just the Newtonian dynamics of this thing, it says that the acceleration of the center of mass is exactly in the direction of the net force, regardless of where those forces are applied. Okay? So in this case, we have a force applied right at the center of mass, that's the gravity, and then we have this tension force applied, off of the center of mass. But that doesn't matter. The direction of the acceleration of the center of mass is in the direction of the net force. So in this case, there's a gravitational force down, and then add to that a slightly weaker tension force up. So the net force is straight down. And so the center of mass will accelerate straight down. Okay? And so it'll just, it'll be as if this thing is rolling along this line. It's like taking it's something that's rolling along the ground and tilting it 90 degrees. And so it's rolling down a wall, basically. And the wall in this case is the piece of thread. Okay, so it's rolling without slipping on that piece of thread is basically what's happening. Okay, so there's that. But there's also a torque. About this point O here, this tension, the force of gravity will exert no torque about the point O, but you have a force of tension applied here. Well, you go this R across that force of tension, and so there's a clockwise torque, or a torque into the board, so a torque in that direction, making this thing spin faster and faster. Okay, so when you write down these equations, if we take, say, down to be positive, and say clockwise to be positive, then we say, well, what's the net force, downward force? Well, the net downward force is a weight, mg, pulling down, subtract the tension pulling up, and that should equal the mass of the object times the center of mass acceleration. So you have that equation for the linear part of this motion. And then for the angular part of this motion, taking clockwise as positive, you have the torque. The torque that's acting about the center mass point there is the radius of the spool times the tension. So that's the torque. And that torque is causing an angular acceleration, alpha. And so that'll be ICM for the spool times alpha. Okay? So you have three unknowns in these equations. There's tension, ACM, and alpha. Three unknowns, only two equations. But remember, this thing that's rolling down here, as the spool unspools the thread, or whatever that's called, it's like rolling without slipping. And so there's a relationship between ACM and alpha, namely ACM is equal to R times alpha. So now you have three equations and three unknowns, and you just solve those, okay, and you get some answer. And the important thing is you find that ACM is less than G. And I think that, ACM is less than G. Yeah, sorry, we didn't actually give a particular one in here. Yeah, ACM is less than G. And so the question is why? Why, just intuitively, why is that the case? Well, there's a couple of ways to think about this. One way is to say, well, look, I've got an object, which is, here's my spool. Gravity is pulling down, but there's another force pulling up. And so if it was only gravity acting, well, then the force is m times g, and you set that equal to m times a. And so a is just equal to g. And so all objects fall, regardless of their mass, fall with exactly the same acceleration g. But this spool of thread is not going to fall with an acceleration g. It will fall with a lesser acceleration. And why is that? Well, you just have to look at this thing. If this tension term were gone, then it would just be mg is equal to macm. ACM is g. But because that tension is acting upwards, it's slowing down the acceleration of the center mass of the spool. Okay, you have also this upward force. And so that's, one way to think about why ACM is less than g. Another way to think about it, which is also really useful, is suppose that this the spool, unrolls from this level to this level. So the center mass of the spool has moved from here to here. So it's dropped down through a height h. Okay? So then clearly there's gravitational field energy, which is being converted into kinetic energy. Okay, and so we have how much gravitational field energy did we get out of this? Well, it's just going to be mgh. So that's how much gravitational field energy we have to put into changes in kinetic energy. Okay? But then there's two components to this kinetic energy. So one of them is a 1/2 m VCM squared. That's the kinetic energy associated with its translational motion. And then plus, there's a kinetic energy associated with its rotation about the center of mass. Okay, so there's a 1/2 ICM times omega squared. Okay, and so you only have, when this thing falls through, say, 1 meter, you only have so much energy to convert into kinetic. If this thing were not rotating and just falling, then only this term would be present. And all of that energy could go into VCM. So the thing would be falling fast. After it's fallen through 1 meter, it'll be moving fast, because all of that gravitational energy went purely into translational motion. Okay? Whereas if that thing has to rotate, okay, so you have this constraint that it's rolling without slipping, basically, down the wall, then you have to have this thing as well. So that means that not all of the kinetic energy can go into translational. Some of it has to go into rotational, leaving less to go into translational. So after falling through 1 meter height, it won't be going as fast, which means that the acceleration is less. Does that explanation make sense? Because that's a really important sort of intuitive thing to understand about things that are rolling. Because not only do you have to get going a massive object, right? Like objects resist changes in their motion. You got to push on that thing to give them translational motion, right? There's inertia. There's resistance to changes in motion. But not only is there inertia associated with the mass, there's also inertia associated with the rotation. Not only do you got to get the spool moving faster and faster down, you also have to get it spinning faster and faster as it's going down. And so that's an additional resistance to changes in motion. So the rotational part of it makes the whole thing more sluggish, makes it greater resistance to changes in motion, and it accelerates more slowly. Does that somehow make any sense? Because if you can get that sort of intuitively, I think that's an important thing to understand about all this stuff. Many important things to understand about all this stuff, but that's a good one. Anyways, oh, look at the time. Okay, I'm going to speed up a little bit here. Okay, so unless any questions on this? The key thing in this is that we have this result from way back when. The sum of the acceleration of the center of mass of any collection of bodies, a bunch of bodies floating out in space, interacting gravitationally with each other and with other things far away and so on. To figure out, any collection of bodies, here they are floating out in space with forces, there's a center mass point right there. And so that whole collection of, the Earth-Moon system, here's the Earth-Moon system, orbiting, here's the Earth-Moon system, and wow, my pen doesn't write anymore. Here's the Earth-Moon system, and they're orbiting about each other. They're orbiting about their common center of mass here. Okay? And so there could be external forces like the sun. Here's the sun. So the sun is pulling the Earth like this, and it's pulling on the moon like this. You just figure out the total force, and that will be the direction of the acceleration of the center of mass, which will be toward the sun. And so then the Earth-Moon system is orbiting, they're orbiting about their common center of mass, and that center of mass point is orbiting around the sun. Okay? Anyways, okay. I think I'm belaboring the point. All right. All right. Let's look at another one over here. And this was this kind of thing, and I was sort of surprised at how many of you didn't get this right. So this has to do with rolling motion. What is the basic idea of rolling motion? So here's an object like this, and this thing is rolling, which means it's rolling along the ground here. It's rolling without slipping. Okay, and that rolling motion, so there's a center of mass, velocity, VCM, and there's an angular velocity, omega cm, center mass point here. Okay, so this thing is rolling along. And so what does that mean? Well, that rolling motion is exactly the same thing as translation. translation with no rotation, okay, plus rotation with no translation. So it means that I can represent that rolling motion, along the ground where the point of contact isn't sliding. I can represent it as translation, where all of the points are moving with the same velocity, and in particular the middle point, the top point, and the bottom point of that wheel are all moving with the same translational velocity. So it's translation without rotation. Plus, I can consider the wheel just sitting there at rest, center mass at rest, but spinning. So rotation without translation. So now the velocity of the center point of the wheel is 0, okay, but the wheel is rotating. Okay, so it's rotating like this. So that point is moving with some velocity to the right, and the bottom point of the wheel is moving with some velocity to the left. And the idea is you want this picture and this picture, when you add them up, all of the points have velocities that correspond to this guy. Okay, and so in this situation, we have, first of all, for example, this center point, take VCM plus a 0. We get VCM. Excellent. Let's look at this bottom point. Okay, this bottom point in this original picture here, this is a point of contact, and that point of contact is at rest. It's not moving. So whenever anything is rolling on the ground, the point of the object that momentarily comes into contact with the ground is not sliding relative to the ground. So the motion is 0. So the point of contact is at rest. So the velocity of that point is 0, which means that VCM plus this unknown velocity to the left has to add up to 0. Well, then this has to be VCM to the left. And so if that's VCM to the left, then this has to be VCM to the right. Okay? And then finally you say, well, okay, but what about the angular velocity? Well, if the radius of the wheel is r, then that angular velocity, omega cm, well, that omega cm has to equal VCM divided by r. Okay, so you have that. So that's one way to think about rolling motion, rolling without slipping. Another way to think about it, which is super useful to have these two totally different ways of thinking about it. The other way to think about it is, well, I've got oh, I can't really use that thing. I thought I had a round thing I could play with here, but I don't. Not really. Anyway, so you've got this wheel, which is doing this, like it's rolling along like this, right? There's a point of contact right now. The bottom is momentarily touching the road, and it's momentarily at rest. If we go a split second before, the wheel is like this. A split second after, the wheel is like this. And so really, what we have is, from a split second before to a split second after, what we have is just a rigid body, namely the wheel, which is being rotated about a fixed point, okay, like this. And so we can think about rolling motion that way as well. And we can think about it as, we have rolling motion is really just this. It's really just a rigid body, the wheel, being rotated about some point, the bottom of the wheel here, with some instantaneous angular velocity, omega point of contact. Why doesn't my thing work? There we go. Omega point of contact. Okay, and so then you think, well, what is that omega point of contact? I know that when something's rotating, when something's rolling, okay, it's got some VCM and it's got some omega cm, and we know the relationship. Okay, so we know the angular velocity about this point is omega cm. But what's the angular velocity about this point? Well, we can figure that out easily enough because we know that speed is VCM. And we know that distance is the radius of the wheel r. And so if you have a rigid body like this, which is rotating like this, then there's an angular velocity about this bottom point. And if you take any point on this object, the tangential velocity is the radial distance times that angular velocity. And so we should have that VCM. It better be true that this VCM is equal to this r times that omega point of contact. Oh, but wait a minute. We know that VCM is just R times omega Cm. So these two are equal. So whenever you have a wheel rolling, you can think of it as at the point of contact momentarily at rest, and the thing pivoting with an angular velocity that's exactly the same as the angular velocity about the center of mass. Okay. Yeah. Anyways, so that was essentially that question. Oh, wait a minute. And then also v at the top. Let's look at the velocity of this point at the top. Oops. I erased my wheel. What's the velocity of this point at the top? Well, the velocity of the point at the top, it's the same idea. You just take this angular velocity down here and multiply by how far it is away. Well, that's r plus r is 2r. So the velocity at the top is 2r times omega point of contact, which is just twice r omega cm, which is just twice vcm. Okay, so the velocity of the wheel, this velocity is 0, this velocity is vcm, and this velocity is 2 times vcm. Okay, top of the wheel moves exactly twice as fast as the center of the wheel. Okay, anyways, that was that question. And one thing, oh, look at the time. Oh, my goodness. Well, let me just say one more thing about this, and then because I know you guys got to go. But so one thing that's nice about this, you can see it all coming together and making sense, because let's suppose we worked out the kinetic energy associated with this rolling motion. So, well, I don't know. There's two ways to think about it. Rolling motion is, point of contact is momentarily at rest, or translation plus rotation. All right, so let's think about those two different ways. So if we're thinking about it as point of contact is momentarily at rest, and we just have an object doing this, well, what's the kinetic energy associated with that object doing this? Well, you just go 1/2 times the moment of inertia for rotating a wheel, not about its central axis, but about a point on the rim of the wheel. Okay, so that's I point of contact times omega point of contact squared. Okay, so let's work this out because it's interesting. So you go 1/2, what's I point of contact? So here I have a wheel. I know what its moment of inertia is for rotation about the center of mass. That's ICM. If I wanted to figure out what the moment of inertia is for rotating about this point, a parallel axis that's located a distance r away, well, I just use the parallel axis there. I just say, oh, that's just ICM plus an mr squared. Okay, and so we have an mr squared term plus ICM times, what's omega point of contact? Well, that's the same as omega cm. Okay, and then you look at that and you say, well, ooh, something weird happened. Sorry, I'm trying to go too fast here. Okay, so what do we get? So then we get equals, this first term is 1/2 times m times r times omega cm squared. Well, r omega cm is vcm. So this is just vcm squared. And the second term is 1/2 ICM omega cm squared. Well, so this is the kinetic energy that's calculated assuming or taking this view of rolling, and this is the kinetic energy. This component of the kinetic energy comes from the translation without rotation, and this comes from the rotation without translation. And so it all works. It all makes sense. Yeah, physics works, right? Yeah. Anyways, okay. I know we have to go. We could talk about many more things, but I hope that was helpful. Does anyone have any additional questions? Anything sort of popping up here? Either about the stuff we talked about, or other questions about the test, or other questions about the course in general. Don't be shy. Maybe you guys aren't there anymore. Let's check. Oh, yes. It looks like you are there. All right. Well, so if there are no further questions, then let me just wish you good luck with all of your exams, including the 121 exam. Remember that there is another prep session. Skylar's going to go a prep session on the Thursday before the exam. I think it's from 3 o'clock to 6 o'clock or something like that. Also remember that there are course evaluations. It's really helpful for you guys to fill out some course evaluations and make some comments and so on, just so how we can improve things and all that. We always like to hear from you. So I encourage you to do that. And yeah, and other than that, just enjoy your holidays. You get a little bit of time off before you're thrown back into the fray in January, and another fresh new 5 courses or whatever. So good luck with everything, and I guess we'll see you at the exam. Bye.